We're continuing our videos on particle physics. In the last video, we showed the derivation and solutions of the Klein-Gordon equation for scalar fields. In this video, I'll go over the derivation and solutions of the Proca and Maxwell equations for vector fields. And in the next video, I'll do the same thing for Dirac-Spinor fields. So in field theory, our main inspiration for vector fields is going to be the Maxwell equations, which describe the behavior of the electric field E and the magnetic field B. These tell us that electric fields diverge or converge around electric charges, and that magnetic fields curl around electric currents. These also tell us that time-varying electric fields can generate magnetic fields, and vice versa. Now, the two Maxwell equations with charge or current sources are called the inhomogeneous Maxwell equations, and it's possible to derive these from a Lagrangian density. To see this, we'll have to spend a bit of time discussing the properties of the Maxwell equations. First, this equation tells us that the B field doesn't diverge or converge, which means B can only curl. This means we can write B as the curl of another vector field, which I denote as lowercase a. This is the magnetic vector potential. Now, if we take the second Maxwell equation and plug this in for B, we can swap the order of the time derivative and the curl, since the curl is made of space derivatives and the order of derivatives doesn't matter. We can group the curl terms on one side. Since the curl of this expression is 0, this vector field only diverges or converges. So it can be written as the gradient of a scalar field, which is the electric potential phi. Solving for E, we get this equation. So we have these two equations relating the E and B fields to the potentials phi and A. Writing out the xyz components, we get these 6 equations. Now, it turns out that we can combine the electric and magnetic potentials into a space-time 4-vector capital A, where the time component is the electric potential divided by the speed of light c. We can also lower the index of A using the Minkowski metric, which adds negative signs to the space components. So with the equations for the electric field, we'll divide both sides by the speed of light c. It should now be clear that we can replace all the potential terms with the components of the 4-potential capital A. Now each of these equations has the same form, a difference of potential derivatives involving 2 space-time indices. For example, this first formula involves the indices y and z. And this formula involves the indices time and x. We'll now label these 6 formulas as the components of a new tensor f, with the 2 relevant spacetime indices as subscripts. This is called the Faraday tensor. In matrix form, the Faraday tensor looks like this. An important property is to notice that f is antisymmetric, which means the matrix transpose is equal to its negative. Another way of saying this is that swapping the 2 tensor indices gives us a negative sign. Now, this is the Faraday tensor with lower indices, but we can also write it with upper indices using 2 summations with the Minkowski metric. In matrix form, the left metric gives negative signs to these rows, and the right metric gives negative signs to these columns. In the end, the B terms get 2 negative signs, so their signs are unchanged. But the E terms each get 1 negative sign, so their signs are flipped. Now, let's look at the 2 Maxwell equations with sources again. It's a fact that the product of the epsilon and mu constants is 1 over the speed of light squared. And that lets us rewrite these equations like this. If we expand these equations using their vector components, we can see the equations can be rewritten in matrix form. And using Einstein summation notation, this tells us that the partial derivative summed with the Faraday tensor gives us the 4-current capital J times a constant. So this is a compact form of the inhomogeneous Maxwell equations. And it turns out that these Maxwell equations can be derived from the following Lagrangian density. Now, with scalar fields, we had this version of the Euler-Lagrange equations. But since the four-potential vector A has four components, we get four different versions of the Euler-Lagrange equations, one for each space-time index. However, we're going to manage all of them at once using a generic space-time index nu. And recall, for the Lagrangian density, we treat all field components and their derivatives as independent variables. So to put this Lagrangian through the Euler-Lagrange equations, we can start by taking the derivative with respect to A sub alpha. Here the derivative terms go to 0, and only the source term with J is left. J does not depend on A, so it can be removed from the derivative. Now, when we have a partial derivative involving two A components, this equals 1 if the components match, and goes to 0 if the components are different, since they are independent. So this gives us a Kronecker delta, which gives 1 if the indices match, and 0 if they are different. Now, the Kronecker delta is basically like an identity matrix that doesn't change the results of a formula. It just has the effect of replacing one of the indices. So this is one side of the Euler-Lagrange equation. On the other side, we have the derivative with respect to partial A. The source term goes away, and we're left with the Faraday term, for which we use product rule. Now, for the derivative of f, we have two derivative terms here. Here we have spacetime indices on the derivatives, as well as indices on the a's. These terms will only be non-zero if both the derivative indices match and the A indices match. So we get two Kronecker deltas here with both index types. When we sum this with f and do all the index replacements, we get f beta alpha minus f alpha beta. Remember, since f is antisymmetric, we can swap the indices to get a negative sign, and this gives us 2f. For the second term, there's a little more index gymnastics involved with raising and lowering indices using the metric, but we also get 2f as a result, giving 4f in total. So overall, the Euler-Lagrange equations give us this. Canceling and rearranging gives us the Maxwell equations we had earlier. So we've indeed shown that this Lagrangian gives us the correct Maxwell equations. Now, since the electromagnetic field is massless, this Lagrangian does not have a mass term. But we could generalize this Lagrangian to include massive fields by adding a mass term here that is quadratic in the field A. This is similar to the mass term in the Klein-Gordon equation that was quadratic in phi. This generalization is called the Proca Lagrangian, and the resulting equation of motion is the Proca equation, which has a mass term. For the rest of this video, I'm going to look at the solutions of the Proca equation, where the mass is non-zero, but the source term is set to 0. This describes massive vector particles like the W and Z bosons involved in the weak force. I'll return to the massless Maxwell version of this field as a special case later in the video. So let's begin solving the Proca equation. Now, the Proca equation is more complicated than the Klein-Gordon equation, since the vector field A has more components. However, our work solving the Klein-Gordon equation has already helped us find solutions to the Proca equation. To see why, we'll do a few algebraic tricks. Let's take the Proca equation and take the derivative with respect to nu on both terms. Now, the F-tensor has the property of being antisymmetric. This means that if we swap the two indices, the result is the same, but with a negative sign in front. Meanwhile, these two derivative operators form a symmetric tensor, meaning that if we swap the indices, the result is the same with the same sign. This is because the order of partial derivatives doesn't matter in calculus. Now, it's a theorem that when we have a symmetric tensor that is completely summed with an antisymmetric tensor, the result is always 0. This is because every term in the summation will always get cancelled out by another term with the opposite sign. If you like, you can think of this as saying that multiplying a symmetric matrix and an antisymmetric matrix together and taking the trace will always give 0. So if we know this summation goes to 0, we're left with this property here for the vector A, which is called the Lorenz condition. Now, this Lorenz condition tells us something important. Although A has 4 components, if we know 3 of them, then the 4th component is automatically determined by the other 3. This means that there are really only 3 degrees of freedom for A, not 4. This fact will become important later. If we go back to the Proca equation and write out the definition of f and distribute the derivative, this term now goes to 0 because of the Lorenz condition. The result is this formula here, which is the Klein-Gordon equation. This tells us that each of the 4 components of the A vector individually satisfy the Klein-Gordon equation. This is good news because instead of having to solve for the 4 component functions individually, we can simply pick one sinusoidal function for all 4 components, and then write down a column of 4 constant scaling components for the 4 space-time directions. All that's left is to determine the 4 constant components of this vector, which I'm going to label using alphas. Now, before we start solving for these alphas, I'm going to review some notation. Remember, capital A is a vector field which is a solution to the Proca equation. And we're looking for solutions with this form of a single cosine wave with a vector of 4 constant alpha amplitudes for the 4 space-time directions. To make this more concise, we can write alpha with a generic mu index, which represents one of the 4 space-time indices. And once again, we can write out a cosine wave as a complex exponential, if we remember the cosine solution is just the real part of this complex wave. It's also common to write the frequency omega over c as the time component of the wave vector, k superscript t. Here, I've also written the 4 spacetime variables time xyz using x's with time xyz superscripts. It's also common to write the 4 spacetime indices using numbers, where 0 indicates time and 1, 2, 3 indicates the spatial xyz directions. It's also possible to lower the indices on k to make them subscripts, if we remember to flip the signs on the xyz components. Remember, lowering the indices of a vector is done with the Minkowski metric, which has minus signs for the xyz directions. Finally, we can write this sum formula between the k's and x's using an implicit Einstein summation over nu. So our Proca solutions for the vector field capital A take this form, and we need to solve for the 4 alpha constants. We can solve for them using the Lorenz condition we saw before, where we take a derivative summed with A and set it to 0. Since the alphas are constant, the derivative can pass by them and just act on the complex exponential. Now, if we were to consider the case where this was a time derivative, which is a derivative with respect to x0, the derivative would only care about the time term in this exponential. And so we get a chain rule term of I k sub 0 out in front. More generally, this derivative in the mu direction will give us a chain rule factor of I times k sub mu out in front. And since the Lorenz condition says this is all equal to 0, we can cancel the complex exponential and get this relationship between alpha and k. So the Lorenz condition basically tells us that the wave vector k and the scaling amplitude vector alpha must have an inner product of 0. Now, to simplify this formula, we're going to take the special case of a wave traveling in the z direction. So the x and y components of the wave vector k are 0, and only the time and z components are non-zero. This means the 4 components of the wave vector k look like this. So from the Lorenz condition, we showed that the wave vector k and the amplitude vector alpha must have an inner product of 0. We can also write this as the row of k components multiplied by the column of alpha components equaling 0. Or we could write out the sum explicitly like this. Now, using the simplified assumption of the wave traveling in the z direction, kx and ky go to 0, so the formula simplifies to this. Now, in this sum, the k's have lower indices and the alphas have upper indices. To make things easier, I'm going to raise the indices of k using the Minkowski metric. This doesn't change kt, but raising the index of kz changes its sign. So our formula now looks like this. And we need to find alpha vectors that solve it. One simple solution for the alphas is to set alpha x to 1 and set all other alphas to 0. As a vector, this solution looks like this. Another solution is to set alpha y to 1 and set all other alphas to 0, which looks like this. The third and final solution is to set alpha x and alpha y to 0 and set alpha t to kz and set alpha z to kt. As a vector, this solution looks like this. Now, you might think that kt and kz are independent values here, but if we recall the dispersion relation for Klein-Gordon waves, the value of kt here is completely specified by kz and the field's mass, so choosing kz fully specifies this vector. We now have 3 solutions to the Proca equation for a wave traveling in the z direction. And since the z direction is arbitrary, this means the Proca equation always has 3 basic solutions for a given wave vector direction. So for the Klein-Gordon equation, once we selected the components of our wave vector k, there was exactly one solution, up to a scaling constant. However, for the Proca equation, after we've selected the components for our wave vector k, we actually get 3 different solutions, which have the same wave direction and frequency, but different constant vectors in front. These constant vectors give different polarizations for the wave. Let's take a closer look at these polarization vectors. In the first solution, we see the wave oscillates back and forth along the x direction as a vector. We call this horizontal polarization. In the second solution, the wave oscillates back and forth along the y direction as a vector. We'll call this vertical polarization. In the third solution, the wave oscillates back and forth along the z direction as a vector, which is along the axis of wave propagation. We'll call this longitudinal polarization. Now, let's forget about the special case of a wave traveling in the z direction. More generally, for any given wave vector k, there will always be 2 Proca solutions which oscillate perpendicular to the direction of wave travel. These are called transverse solutions. And there is also the third Proca solution, which is longitudinal polarization, which oscillates in the direction of wave travel. Now, you might see the 2 transverse polarizations rewritten in different ways. For example, way back in video 3, I showed that we can combine the horizontal and vertical polarizations in different amounts and different phase delays to get other types of polarizations, such as left and right circular polarizations. So you might see these 3 basic polarizations written as left circular, longitudinal, and right circular. These are also called spin 1, spin 0, and spin -1 polarizations. Okay, so we understand that with the Proca equation, if we choose a wave vector k, we get three basic solutions. But an important observation is that the Proca equation is linear, just like the Klein-Gordon equation. So the sum of any two Proca solutions gives us another Proca solution. So to get the most general solution to the Proca equation, we do the following. We start with one basic sinusoidal solution with a wave vector k. Just like the Klein-Gordon equation, this wave vector must obey the dispersion relation. This means that, given the xyz wave numbers, the time component of k, which is the frequency, is already determined by the field's mass. Now, we can add any number of sinusoids together to get another solution. So we can do an integral over all possible wave numbers kx, ky, kz, and give each one its own complex amplitude, curly a, that depends on the wave vector. This complex number includes both amplitude and phase information. And finally, each basic wave can appear in one of the three polarization vectors, which I'm denoting as epsilons 1, 2, and 3. So we must also include a summation over r from 1 to 3 for the polarizations. The amplitude curly a for a given wave should depend on both the wave vector k and the polarization r. If we take the real part of this is the most general solution to the real Proca equation. The next thing I'll do in this video is discuss the solutions to the Maxwell equations, which is a special case of the Proca equation where the mass is 0. This seems like a small change, but the massive and massless solutions to the Proca equation do have some important differences. First, since the Proca equation is massive, the dispersion relation tells us that the phase velocity of each basic wave solution is different depending on the wave vector. But for the massless solutions, all wave solutions travel at the same speed of light c, regardless of the wave vector. The biggest difference between the massive and massless cases is that the massive case has three possible polarization solutions, whereas the massless case only has two transverse polarization solutions, and there is no longitudinal polarization. To see why this happens, let's discuss gauge transformations. Now, with our potential formula for the electric field, in the special case of electrostatics, the time derivative part goes to 0, and the E field can be written as the gradient of a scalar function phi. This leads to a special property where if we transform the potential phi by adding a constant value k everywhere, then when we take the gradient of the transformed version, the gradient of a constant k goes to 0, so the result is unchanged. This means that the electric field E is completely unchanged by this potential transformation, in the special case of electrostatics. This means that there are multiple possible phi potentials that give the same electric field and the same physics. In the full electrodynamics case, we've rewritten the E and B fields as the Faraday tensor F, shown here. Now let's transform the 4 potential A by adding the gradient of a scalar function, partial mu lambda. Now if we take our Faraday formula and transform A this way, after we distribute the derivatives, the lambda derivatives cancel, and the formula remains unchanged. So here we see that the F field is completely unchanged by this transformation of A, and there are multiple possible A potentials that lead to the same F field and the same physics. We call these type of field transformations that leave the physics unchanged gauge transformations, and the specific choice of A potential is called a gauge. Now, I want to take a moment to talk about the different types of transformations we can do in physics. Let's say we do some type of physics experiment with electricity and magnetism and record the results. The next day, we rotate the experiment setup 90 degrees and do the same experiment. We would expect to get the same result. This is because the laws of physics in our universe do not depend on spatial direction. In other words, the laws of physics have rotational symmetry. In terms of the mathematics, we can see rotational symmetry in a given Lagrangian density if we rotate all the vectors and tensors in the Lagrangian density by 90 degrees, and see that the Lagrangian density is unchanged. This means that the action S, which is the integral of the Lagrangian density, is also unchanged. So the principle of stationary action will give equivalent results. Now, we recently discovered a type of transformation on our electromagnetic 4 potential A, which leaves the Faraday tensor F unchanged, and therefore leaves the Maxwell Lagrangian density and its action S unchanged. You might think that this is pretty similar to our example of rotating our experiment setup. However, there is an important difference between the two. When we rotate our experiment 90 degrees, we're actually changing the physical state of the experiment, which we can measure using physical coordinate axes. But when we gauge transform our 4 potential A, we're not changing the physical state of the experiment. This is because the 4 potential A is not directly measurable. Only the electromagnetic field F is directly measurable. So when we gauge transform A, we're not changing the physical state. We're just changing to another mathematical description of the same physical state. And that's what we mean by gauge transformation. It's a change in mathematical description for the same physical state. Now, let's see what happens when we take the Proca Lagrangian and apply this gauge transformation. We've shown that when we do this transformation on A, the F tensors are left unchanged. But the mass term contains A's that will get transformed. If we distribute all this out, we see that we keep the mass term, but we get 3 extra terms added onto the Lagrangian. So this transformation changes the Lagrangian and would change the physics we observe for the field. However, if we set the mass term to 0, it disappears and we get the Maxwell Lagrangian. Since a gauge transformation leaves F unchanged, this means the Maxwell Lagrangian is completely unchanged by a gauge transformation, and the physics of the field will stay the same. Now, here we've left out the Maxwell source term, but even if we include the source term and gauge transform it, we can use product rule here, and this first term goes to 0 as long as the current J obeys a continuity equation. And this second term is a divergence term, which means it will go to 0 when we integrate the Lagrangian density to get the action S. So even if the Lagrangian is changed here, the action S is not, so the physics is unchanged. So this is a fundamental difference between the Proca and Maxwell Lagrangians. With the Maxwell Lagrangian, we can do these gauge transformations on the field A and still get the same physics. But this is not true for the Proca case. This is a subtle but important difference between the Proca and Maxwell fields. For example, we saw that with Proca fields, the Lorenz condition is a mandatory property. But for Maxwell fields, the Lorenz condition is not automatically true. Instead, we can do a gauge transformation on A to make the Lorenz condition true by using a clever choice of lambda in our gauge transformation. This freedom to gauge transform A without changing the physical situation is the reason that longitudinal polarizations no longer appear for Maxwell fields. Let's see why. We'll start with a longitudinal wave traveling in the z direction. So the wave covector k looks like this, where only the time and z components are non-zero. And for the longitudinal polarization, the field vector itself only has time and z components, so it points along the direction of wave travel. Because Maxwell waves are massless, the dispersion relation tells us that the time and z components of the wave vector must be equal, up to a difference in sign. We'll choose the plus sign and set kz equal to kt in both the exponential wave and the polarization column vector. Now let's do a gauge transformation on A. we'll use a field lambda that looks like a plane wave times the imaginary I. In our gauge transformation formula, this derivative here represents 4 spacetime derivatives that we can arrange in a column. Now, one inconvenience here is that the derivatives have upper indices. We can lower the indices if we remember to flip the signs on the xyz components using the Minkowski metric. Now the time derivative brings down IKT, and the z derivative brings down negative IKT, meaning these two negative signs cancel. And the x and y derivatives give 0. Now the time and z components each have a pair of complex i's, and multiplying them gives us negative 1s. Finally, subtracting these two terms gives us the 0 vector. So what we've shown here is that anything that looks like a longitudinal wave is actually equivalent to the field equaling 0 everywhere, because the two field configurations are linked by a gauge transformation that does not change the physics of the situation. Both gauge choices lead to the same electromagnetic field. So for our massless Maxwell field, the fact that there are multiple gauge fields A that lead to the same physical situation means that longitudinal polarizations in the vacuum do not exist. Only transverse polarizations exist. This is why electromagnetic waves in the vacuum only have transverse polarizations, and no longitudinal polarization. As an aside, something similar happens in the case of gravitons, which are spin 2 particles. Massive spin 2 particles normally have 5 polarizations, but for the massless case, like gravitons, only the +2 and -2 polarizations exist, which are equivalent to the plus and cross polarizations for gravitational waves. You can check out my videos on gravitational waves if you want to learn more. The last thing I'll cover in this video is the notion of vector particles and antiparticles. This will largely be a repeat of the explanation of antiparticles in my Klein-Gordon video, so if this explanation goes too fast, you can review that video. So with the Klein-Gordon field, we found that if we made the scalar field phi complex, and wrote this Lagrangian with phi star phi product terms, we actually doubled the number of solutions. We found taking the Euler-Lagrange equations and varying with respect to phi star gave us a phi Klein-Gordon equation with particle solutions. And varying with respect to phi gave us a phi star Klein-Gordon equation with antiparticle solutions. We also saw the U1 symmetry of the Lagrangian led to a conserved current by Noether's theorem, and this was the electromagnetic current. The exact same thing happens if we take a look at the complex version of the Proca field, by including complex conjugate terms in the Lagrangian. Taking the Euler-Lagrange equations and varying with respect to A star gives us the A Proca equation for particles. And varying with respect to A gives us the A star Proca equation for antiparticles. This Lagrangian also obeys a U1 symmetry. So if we give every A a positive phase and every A star a negative phase, they all cancel out, leaving the Lagrangian unchanged. This leads to this conserved current here, which again is the electromagnetic current. So when it comes to real Proca fields, these are for vector particles that are their own antiparticle and have 0 electric charge. This describes the photon, which has 0 mass, and the Z boson, involved in the weak interaction. Complex Proca fields are for vector particles where the particle and antiparticle fields are distinct, and the particles do have electric charge. The main example here is the W bosons, where the W plus and W minus bosons are particle-antiparticle pairs, described together by a complex field. Now, keep in mind these Lagrangians are for free particles with no particle interactions. The Lagrangians would get much more complicated if we included particle interaction terms.